Okay, so this lecture is meant to introduce you guys to the idea of uniform circular motion. We've looked at the concept of just moving one-dimensional or moving two-dimensional and what causes these types of movement in terms of forces and what happens when we collide and energy, stuff like that. So now we're going to take a very specific case of when things move in a circle. Okay, so this is called circular motion. This is a terrible marker. I should test it out first. This is circular motion. And we are specifically going to look at the concept of what's called uniform circular motion. And this is defined as when an object is moving in a circular path at constant speed. Now, even though it's moving at a constant speed, the object is actually still accelerating, and that's because acceleration is a change in velocity, not just a change in speed. So velocity has both speed and direction. So as an object is moving in a circular path, so I'll just kind of think about an object, and it's like moving around in a circle. So if I've got like a ball in the end of a string, and I'm moving around in a circle, its velocity is initially in this direction. Tangent to the circle, to the circular path. And then in the next moment, its velocity is, the object is here, and in the next moment, its velocity is going in that direction. So its velocity has actually changed direction. So the speed is constant, but the direction is continually changing, so there is an acceleration. So the speed is constant, direction is continually changing. So there is acceleration. But it's a very specific kind of acceleration because it's not an acceleration that's changing the speed of the object. And those are the kind of accelerations we've been studying for. All of our forces we've been looking at causing a change in acceleration. It always changes the numerical value, but in this case it's changing the directional value. So we call it a specific type of acceleration. This is called centripetal acceleration. And this word centripetal acceleration actually kind of means center of the path, center seeking acceleration. And if we kind of think about what's happening to our velocity vector here, my velocity vector is initially in this diagram. It's initially pointing this way. And then something kind of like shoves it. Something pushes it this way. Remember, accelerations are always caused by forces. And force can be thought of as like a push or a pull. So if initially my velocity is going in this direction, and then something pushes it that direction, it's almost as if like there's some force that's like pushing it that way to cause that directional change. And so the centripetal acceleration is always an inward acceleration in the sense that it's pushing that velocity such that it is rotating kind of along with the circle. Okay, so centripetal acceleration is an inward acceleration. Acceleration caused by a net inward force. I'll kind of talk about this nuance in a moment. Okay. So in terms of like symbol, I'm going to erase this a little bit here. I guess I should kind of think about the boards being in half. So the symbol for our centripetal acceleration, again, again, it's a very particular kind of acceleration. So we're going to call it A sub c, centripetal acceleration. The equation for it, it's not your standard change in velocity over time because, again, numerically our velocity isn't changing. But centripetal acceleration is equal to v squared over r, where v is just the speed of the object. And again, it's got to be moving in a circular path. And r is the radius of the circular path. And again, in physics, our standard measurement for distance is going to be in meters, so your radius needs to be in meters. Now, and the units would just still be meters per second squared. And you can kind of see how that would shake out. If I square my velocity, it's going to be meters squared per second squared divided by a distance of meters that shakes out to meters per second squared. Now, sometimes when we are looking at circular motion problems, we actually have to figure out what the velocity of the object is. And if we think about finding velocity of something moving in a circular path, so if I've got this object and it's just going around and around and around like in a circular path, if I measure what's called the period of the motion, then I should be able to figure out the velocity of the object. So we've studied the idea of period when we did the lab springs the thing. And remember when you would pull down the spring and you would measure like how many times it goes up and down? We recall that a period is the time for it to make one complete movement. So in the case of the spring, the period was it went down and then it came back up. We're going to see later on that for like a pendulum, for like a swing, a period is to go to and fro. So for something moving in a circular path, the period is the time for one revolution. And the symbol for it, because it's a very specific amount of time, so it's going to be a capital T. And then the units are just measured in seconds. Now, if we know the period, let's go back to our base definition of velocity, or speed. Velocity is just how quickly something travels a certain distance. Well, if I think about the distance of something going in a circle, like start here and I go all the way around, that distance is just the circumference. So for an object moving in a circular path, distance traveled is just going to be circumference. Therefore, the velocity of something moving in a circular path is just going to be our equation for circumference, which is just 2 pi r over the period. Now, this would just be measured in meters per second. Oftentimes when we talk about things that are moving in circular paths or they're rotating, sometimes the units we have meters per second, but sometimes we have what are called RPMs. Okay? And an RPM is the same thing as a rotation per minute. So that is another way of saying, well, my speed is just going to be one rotation is 2 pi r, but in this case, the time value is 1 minute. Okay? So I think there are a few problems in your text where you're given the value of speed in RPMs, and you'll need to go ahead and figure out, well, what is the circumference, what is that value of that rotation in meters, and then divide by per minute to get it into meters per second. Okay? So that's another way to kind of find the velocity of an object moving in a circle. Now, in the previous statement here, I said that the centripetal acceleration is an inward acceleration that's caused by a net inward force. And so that force is called the centripetal force. So the centripetal force is the net, I'm going to quotation it, the net inward force that causes an object to move in a circular path. Now, I'm not going to list a symbol for the centripetal force because there is no symbol for the centripetal force. Centripetal force is not a new force. Centripetal force is one of the forces we've already studied that is causing an object to move in a circular path. And so this is something that once you create your force diagram, you're going to look at your force diagram and you're going to think about, okay, which of these forces that I've identified is what's actually causing my object to stay in a circular path, which is causing this. And it may be a singular force, it may be a combination of forces, it may be a component of a particular force. So it just depends on the situation in terms of which is the centripetal force. So I want to kind of go through just a few situations, examples, so you understand what I mean when I say this is a net inward force, okay? So there's a couple kind of classic examples of things moving in circular paths. One of them is just a car moving around a circular path. So if we can kind of envision, here's like my little track, and then here's my car. And it's moving like that way, okay? Now, it's easiest if we kind of think about this. Well, you've got the weight, you've got the normal force, you probably have some force of like an engine, and you have force of friction. But what we want to think about is when it's actually moving in that circular movement. So right now here's kind of like the straightaway. So there's no centripetal force. There's something that's causing it to stay in a circular path. But as this car kind of rounds the bend here, so that's the perspective I'm about to draw. The car is going along and it's coming like almost out of the whiteboard, like rounding this curve. Okay, so that's the perspective that I'm going to draw. So there's the headlights, there's the like little wheels, there's the grill. Okay. So it's coming like at you right now. Let's draw a windshield, huh? So when I think about it from this perspective, I still have weight and I still have normal force in this perspective. Like my weight is still going down, my normal force is still going up. In terms of my other two forces, those would be in the Z direction, in the sense that like the force of my engine is actually like coming out of the board and my force of friction is actually going into the board. But there, when you round a curve, there's another force that's actually causing you to stay in that curve. And it's kind of easiest to visualize if we don't have that force. Like if you're trying to go around a curve and there's no friction, you slide out of the curve. But if there is friction, you stay in the curve. And so there's actually a force of friction that is maintaining your ability to stay on the road in that circular motion. Okay? So if I think about in terms of like X, Y, and I could even go further and say Z, like directions. In terms of, and again, if this is my Y, X, and we kind of get like the Z direction. In terms of my X forces, I only have this friction. For my Y, I've got normal force and weight. And for my Z, I'd have this force of engine, and I have an additional friction that is like opposing like my forward movement in the car. So in the case of setting these things equal to MA, each of these is equal to their own MA value. Well, we know that if the car's not like moving up and down on the road, that the AY here is 0. Whether or not there's a Z acceleration depends on if you are actually speeding up or slowing down. So this is it may have a value, it might be 0. But in terms of the X direction, there's no other force in the X direction. It is just this frictional force, according to my diagram. So in this case, this right here, let's make it blue. This right here, this is my net inward force. Like this is the force that's causing the car to go in a circular path. If you didn't have friction, the car, like as it would turn, it would just fly off. Okay? This is my net inward force. So in this case, this is my centripetal force. And this would be my centripetal acceleration. So for our car going around a curve, the frictional force is the centripetal force. Let's look at another example. Let's take it back to elementary school and look at tetherball. Okay, so we've got our visual, there's our tetherball, it kind of swings around like this. So again, starting off with just what our forces are. It's here on the Earth, so it has this force of gravity, it has a weight value. There's a rope holding the tetherball, but it's at an angle. So there's my tension. And if my rope is at an angle, I would just immediately know, oh, I've got to break this up into components. This would be a Tx. This would be a Ty. Again, if I thought about this and said, okay, well, horizontally, I've just got Tx. Vertically, got Ty, so this would be Ty minus weight. The second law says 0 equal to Ma, so Max, My. In this case, if the ball is not accelerating up or down, this will be equal to 0. But there's nothing that's canceling out this Tx. This Tx is an unbalanced net force. So in this situation, Tx is my inward force. It is my centripetal force. Which means that this is my centripetal acceleration. Okay, let's get one last example. And as we go through class, we will look at lots of different examples, but these are kind of some of the classics, the greatest hits. We'll call it the loop-de-loop. So roller coasters. Okay? So if we kind of think about this. So here you are on the roller coaster. Super excited. Well, your eyeballs are weird. You're really excited. When you get to here, you're upside down, and we're going this way. And then you come back around. Maybe you're not too happy about that last loop. Okay, so forces. I've got, well, let's be consistent. I've got weight in both situations, regardless of where I am on the roller coaster. I've got weight. If I'm at the bottom of the roller coaster, my support force right here is holding me up. At the top of the roller coaster, this support force, you're kind of thinking about, but it's right, there really isn't a support force. Like, why would it be upside down? If there was no support force, okay, let's do the what if. If there was no support force here, if there was no normal force, as like your little car would be coming up here, if there was no normal force, you would go flying up. Like, the track is what's keeping you from like flying out and off into who knows where, okay? So the normal force is supporting you, it's preventing you from moving up any further. So you are actually exerting this contact force onto the surface, and it's exerting it back onto you. Now, the one thing that we haven't been drawing on our force diagrams are the accelerations. And this one, it's kind of important to see that. Remember, centripetal acceleration is the net inward acceleration. So at the bottom of the roller coaster, the centripetal acceleration is pointing up, but at the top of the roller coaster, the centripetal acceleration is pointing down. It's always pointing towards the middle of the circle. It's inwards. So if I think about this, for the bottom, if I think about my net force, I only have vertical forces. Again, the direction of your acceleration is always positive. We've learned that in previous chapters. The direction of acceleration is always positive. So in this case, my normal force is going to be considered positive. So normal minus weight, that's my net force. That's my dot, dot, dot. And that's going to equal MAC. But for the top, this is going to be, well, they're both pointing down, and they're both pointing in the same direction as the centripetal acceleration. So they're both positive. Normal plus weight is equal to MAC. And kind of like, well, what does that mean? Let's just solve for normal force. Because remember, normal force is what the floor or a surface is exerting on you. And 99% of the time, it matches your weight, and that's what you're used to. That's what's normal for you, right? But when you have an acceleration, all of a sudden your normal force doesn't necessarily feel normal anymore. So let's look at what's happening to your normal force as you're going through the roller coaster. So if I took the bottom equation and I solve for normal force, that would entail me adding this weight over here to this side. So this is going to be MAC plus my weight. I'm just going to convert that. Equation for weight is mg. So this is saying that my normal force, now remember, normally your normal force is just equal to mg. That's what you're used to. But when you are going into a roller coaster and you're at the bottom of the loop, it's your normal force equal to your MA, the acceleration you're experiencing, plus the mg. This is why you feel heavier when you like go down that bottom little bit of a curve, okay? And it could be any type of a curve. So just even like when you are like going down 3rd Street and at the very bottom there is a slight circular motion where like you are curving to go flat, right? You're going from this incline to flat. There's a slight bit of curvature there and you feel heavier for that little bit of time. That's because you're experiencing a centripetal acceleration and your normal force is going to be equal to the mass times your centripetal acceleration plus your mass times gravity. You feel a little heavier. Let's look at the top. If I did the same thing and I solved for the normal force at the top, in this scenario, I have to subtract my weight over. So this is going to be MAC minus my mg. So again, you're used to, your normal feeling is when your normal force is just equal to mg. But now we're saying, no. We're going to actually take that value and make it smaller. Okay? And so you feel that way. When you're like in a loop-de-loop and you're at the top, you feel that like almost weightlessness experience because the normal force is no longer what you think of as normal. Okay? So again, the centripetal force is not a new force. Notice, in all of my diagrams here, I have not labeled a new mystery centripetal force. It's just one of the existing forces in your force diagram. In fact, it is the force or combination of forces that is causing you to move in a circular path. So in this case, with my tetherball, really it's only the horizontal component of tension that's causing it to stay in a circular path. The vertical component of tension is just countering weight. With my roller coaster, it's a combination of forces. In the case of at the bottom, it is subtracting the two. At the top, it is an addition of the two. Okay? So it's one of your existing forces, combinations, components. It's one of those forces that's causing it to stay in a circular path. Okay? So we will do, when I get back, we will do some actual in-class examples and do some mathematics of this.